All right, hello. Today I will be showcasing this circuit here. What this circuit is a 3-bit counter. So we're going from 0 to 7, all right? And it will be asynchronous to the clock, all right? And we've seen a lot of these in the slides in the video lessons. And what makes this circuit different than from those circuits that we've been seeing in the lessons is that in the lessons we've usually been seeing, obviously since it's asynchronous, we're seeing this clock go into the first clock input of the flip-flop, but we can see that the other clock inputs aren't getting that clock input. That would make it synchronous. But because this is asynchronous, we would have usually have seen this Q output right here being sent and going into the input of the clock inputs of the next flip-flop, and so on. This one would go to that input. But what makes this one different is we're not just taking the Q's output and throwing it into the clocks, but we're taking the inverse of the Q output, or the complement, I should say, and we're sending that to the clocks. And now what does that do? That's going to, instead of counting down from 7 to 0, we're going to see it count up from 0 to 7, all right? So let's go ahead and demonstrate this circuit here. All right, I'm just going to step through till we get 0 here. Everything seems so far it's good. There we go. We get our first number, which is 1, or second number, I should say. And then going from 1, we should be counting up, but we went back down to 0. Now, this is a glitch, all right? And what a glitch is just the wrong output being sent out. Now, is this truly what our output should be? No. And I could show that if I just keep stepping through, we're going to get 2 eventually. All right. And you can see if we go from 2 to the next number, we have no glitches. It goes straight to 3. And I'll show one more time. From 3, we should have a glitch. We went back down to 2, back down to 0, and now we hit 4. So what's going on here? We have 3 T flip-flops here that each experience propagation delays. And each flip-flop here, this middle one and this bottom one here, are both dependent on the output of the first flip-flop. So when you think about it, going from an even number to an odd number, starting at the even number, our least significant bit will always be 0. All right, so when we go to an odd number, all we're changing is just that first least significant bit. That's why we're getting no glitches going from an even number to an odd number, because all we're changing is the first bit from this first flip-flop. None of these other flip-flops really are changing. But when we're going from an odd number to an even number, that is where we'll see the glitch, because then we're going to have to see these bits here, bits 2 and 3 having to change, and that's going to be dependent on the first flip-flop here, and we're going to be experiencing propagation delays. So that's why we're seeing a wrong number before we see the right one, or sometimes even 2 wrong numbers before we see the correct count up. So that is why that is happening. If we were to use 5 flip-flops instead of 3 here, for example, how high would we be able to count? We would be able to count up to 31. And that's simply due to the fact that each flip-flop here almost represents a bit place. So here we have 3 bit places, and 3 bits gets you 1 plus 2 plus 7. That's 2 to the 0th power, 2 to the 1st power, and then 2 to the 3rd power, and that equals 7. With 5 bits, it would be the same thing, 2 to the 0 plus 2 to the 1st plus 2 to the 2nd, all the way up to 2 to the 4th power, because 0 through 4 is 5 numbers there. And that would total out to be 1 plus 2 plus 4 plus 8 plus 16, which is 31. You can check my math there. I'll go ahead and just cycle through the rest of this real fast to show you that it does count up to 7. And there we go. And from 7, we're glitching, and then back to 0. Okay, awesome. So that is our circuit here. Now let's go ahead and move on to the next circuit. All right, so here is our next circuit, and as you can tell, it is very similar to the recent circuit that I have showed you. All right, but the only difference here really is this little strobe that we have here. And what a strobe does is it acts as a buffer for the output so that it won't show any of these glitches, all right? This is specifically a tri-state buffer, and it's useful because it has a high impedance state. So in theory, instead of a correct signal going to a wrong signal, in our last case, we had a odd number going to a positive number, but it would show some glitches, a lot of wrong numbers. This time, we're going to go from an odd number, a correct signal, odd number, and then it's going to show no signal instead of a glitch, or in other words, a high impedance signal, before all the flip-flops are updated, and then will we see the correct output once everything has been buffered through. All right, so I'm going to go ahead and just simulate through this. I'm going to turn on auto propagate, and I believe all my settings are working fine. So you can see that we're getting no glitches going from an odd number to an even number. And that is thanks to this tri-state buffer here. All right, so I'll go ahead and leave it off there. Thank you so much for watching, and have a good